All right, it says, what is the concentration of H3O plus and the pH of a 0.35 molar HF solution? The Ka of HF is 3.5 times 10 to the minus 4. So the first thing is we need to write the Ka expression. I don't know if it's the first thing, but we need to write the Ka expression. So the Ka expression is products over reactants, H3O plus, F minus, over HF. Notice that water is not included because water is a liquid. Ka is the same as Kc, except it's for acids, right? So this is, in this case, this is an acid. But in this case, we're looking at using an ice table. So an ice table is initial change in equilibrium, and you'll notice that the ice table has all of the aqueous stuff in it, not the water, because its concentration within reason is constant. So it says, what is the concentration of H3O plus at pH of a 0.35 molar HF solution? So initially, the concentration of HF is told to us at 0.350 molar. All right, I'm not going to rewrite the molar because the molar is here. The initial concentration of H3O plus and F minus is 0. So this is 0 and this is 0. Well, how are we going to change these things? We're going to add a certain amount. In this case, we're going to add X amount of this. We're going to we're going to subtract X amount of this because we're going to lose some of this HF when it forms H3O plus and F minus, and we're going to gain X of this and gain X of this. So we're always losing losing reactants by subtracting and gaining products by adding. So at the end of the day, we get 0.350 minus X, X, and X. So we have a Ka expression, and we at least have variables that are constant, right? They're all x's. The other thing is that this x we can usually ignore. If this x is less than 5 or 10% of this value, then we can ignore this. If we don't ignore this, then we have to use the quadratic equation. All of the examples I'm going to go over on this sheet, you can ignore this x, okay? Technically, you could check at the end. So we have the Ka expression. So now let's plug in what we know. Well, we know Ka. Ka is 3.5 times 10 to the minus 4. That's given to us. The concentration of H3O plus at equilibrium, because remember this is an equilibrium expression, so we have to deal at equilibrium, not initially, is X. The concentration of F minus is also X. And the concentration of HF is 0.350 minus X, but we're saying let's ignore that X. So it's just 0.350. All right. So now what we need to do is we need to cross multiply, and we find that X squared is equal to 0.350 times 3.5 times 10 to the minus 4. And when you do that math, you get 1.2 times 10 to the minus 4. Now, take the square root of both sides, all right, and you get X equals, only the positive answer because it's molarity, 1.1 times 10 to the minus 2 molar. This is exactly the same as you did before for Kc values, except now we're doing it for acids. So what is this actually? Well, this X is equal to the concentration of H3O plus. So now there's one additional step that you haven't done before. And the additional step is to find the pH. Well, we remember from the previous questions that pH equals the negative log of the concentration of H3O plus. So in this case, the pH equals the negative log of the 1.1 times 10 to the minus 2 molar. And the pH is equal to 1.96. All right, and if you were to actually test this, you'd find that this X is about 3% of this. All right, so therefore it was okay to ignore the X. But in all these examples, you're able to ignore the X and you don't have to use the quadratic equation. Again, the only difference between this and the previous chapter, this particular question in the previous chapter, is you have to go ahead and take your X, which is your concentration of H3O plus, and plug it into pH equals the negative log of the concentration of H3O plus.